Okay, now we are in our last day of this unit, and we're going to work with densities and molar masses and stoichiometry. So you guys have worked with all of this before. We're just combining it all together now. So with gas density, the big thing to know about density is, first of all, it's going to be mass per volume. We know the formula for that. But at this point, we've really talked about densities of solids and liquids. Well, if we're doing that, we're usually going to use units such as grams per milliliter. But when we work with gases, those gases take up a much greater volume. They spread out. So the units that we're going to want to work with are grams per liter. And the other thing we want to mention here is that there's another difference with gases, and that is that they can be compressed. So all of those variables that we've been talking about, pressure, volume, temperature, and number of moles, if we change those conditions, that's going to change what's going on with our gas densities quite a bit. So here we have this formula written on our paper. It's nothing new for us. And we see this unit. Density is in grams per liter. That's what we want to remember. Density is grams per liter. Then we jump to another familiar one, which is molar mass, formula weight. It's all the same thing. And the important thing to remember here is that when you're calculating this mass, it's always the mass of 1 mole. So here is our molar mass. And these seem like simple little things, but we have to remind ourselves to use them sometimes, and then you have to think about what those units are. And if you write that information at the beginning of your problem, I think it's really going to help guide you in which direction you need to go. Okay, so gas constant, we've also got this memorized probably. It'll be given to you on your quiz, but you probably have it memorized. You should at least be able to use these units. Here's the formula. Okay, so our first example, pretty simple. It just says, what is the density of methane at STP? So we are looking for density. What units would I get density in for a gas? Grams per liter. So there's our density that we're looking for. And again, if you write this down, we just have to think about the dimensional analysis and getting grams on the top and liters on the bottom. Uh-oh, I don't really have any numbers to work with, but what do we know? What could we think about? Okay, I heard two things. I heard molar mass and I heard STP. Both of those are beautiful. So I look at that. It tells me what the gas is. So if it's methane, I know the molar mass. I add it all up, and I get 16.05. What units should I write down? Grams per mole. Okay, I'm halfway there. I'm pretty pleased about this. I've got my grams in the numerator already, so all I have to worry about is getting moles out of the denominator and making that change into liters. Can we do that? Of course we can, because it's a STP, so that's easy. Always take the simple route if you can. It says it's a STP, so all I need to do is say 1 mole of any gas at standard temperatures and pressures has a volume of 22.4 liters. That is it. If you had plugged in values, standard temperature, standard pressure, you would get exactly the same answer. But why take the long way when you can take the easy way? How many sig figs do you think? This is a tough question, actually. Let's go with 3. I'm going to go with 3. You notice that you're not given any values here for sig figs. Here we have 3 sig figs. Here we have 4 because our rule for formula mass or molar mass was to round to 2 past the decimal. I don't typically let conversion factors dictate or limit my significant figures, but really we did round this to 3 sig figs. That's a rounded value. So let's go ahead and keep that at 3 sig figs. And anybody get an answer? Excellent. And then that's going to be in grams per liter. Always a good idea to look at those numbers and make sure it makes sense. We know the density of water is 1 gram per milliliter. I would expect a gas to be quite a bit less, so less than 1 gram per liter. That sounds reasonable to me, so we probably did it correctly. Okay, number 2. Here we're looking for molar mass. What units would I get molar mass in? Grams per mole. And we know that the gas has a density of 1.25 grams per liter. Okay, so we've got grams in the numerator already. We want to make our liters go away and go to moles. And again, we've got this right here. So because of that, we can say 1 mole of the gas has a volume of 22.4 liters. This is only possible because it's at standard conditions. If it's not standard conditions, you cannot use that number. But you'd have to have some other information, yeah. Okay, so we calculate it, and to 3 significant figures you come up with. Point what? 0? And that is in grams per mole. That's molar mass. What do you think a possible gas, what do you think this could possibly be? What if I told you, hey, it's a diatomic element? Nitrogen, good. So, could be, you'd have to be given more information, but it could be nitrogen, N2. Okay, number 3. Here we're given grams of a gas. We're told that it exerts this pressure in this volume container at this temperature. And what we want to do is we want to calculate the molar mass of the gas. So in this case, you guys already have done one of these. You've done a couple of these. So there was on homework 52, I think it was, we threw, I don't remember how many, 1 or 2 on there, just to see if you guys could figure it out, because you know how to calculate molar mass. You know how to work with Pivnert, so there's no reason you couldn't do this problem, solve for moles using your Pivnert equation, and then just take your grams divided by the moles that you solved. I'm going to do it a little bit differently here. Here we're looking for molar mass. I'm just going to do this in one big problem so that I don't have to write numbers down. So if we're looking for molar mass, what units are we trying to get it to? Grams per mole. And I'm just going to start writing some things down. So I see that I've got 2.94 grams. Well, I need to also get moles in there. Where can we find that unit? What might we think about plugging in now? I haven't brought it up yet today. Excellent. So the gas constant. So we remember that our gas constant, R, is 0.08205 atmospheres, liters, over mole Kelvin. So in this case, I want moles in the denominator. So should I keep my gas constant as is, or should I flip it? As is, because moles is in the denominator, so it's perfect the way it is. So 0.08205 atmospheres, liters, over mole Kelvin. So here's the beautiful thing about dimensional analysis. I don't have to memorize any formulas. All I'm trying to do is get things to magically work the way I want them to work. I want grams in the numerator, moles in the denominator. I've got it. I've got some other stuff in there, so my goal is make the other stuff cancel out. That's all you're trying to do. So I read through. First thing I come to is my atmospheres. Here I've got it in the numerator, so I put it in the denominator. So atmospheres is gone. I see some liters. Over here it's in the numerator, so again, I need to put it in the denominator so that it cancels. So liters are gone. Last thing, we have some temperatures. So 265, anybody do that conversion real quick? Thank you. 538 Kelvin. So since I've got it in the denominator, I need to put it in the numerator so that it cancels. Everything has canceled except what I circled in green. My grams on the top, my moles on the bottom. Throw a 1 in there if that bothers you. And again, this is going to be the 3 significant figures. Thank you. 127 grams per mole. That looks looks reasonable to me for a molar mass. If I got something like 6,000, I'd probably question myself, but 127, that looks reasonable. Okay, so you guys have just tackled example number 3. We have one more of these type, so moving on to example 4. Here we're looking for the density of methane. This sounds familiar, but what's different? Which is not STP. Instead, we're given the other values, so we just need to go through that same sort of process. If we're looking for density, we're looking for grams per liter, and it's methane. So I think sometimes this might be the hardest thing for people to think about. You have to be able to look at that and think to yourself, wow, from that, I know my molar mass. I know to start with 16.05 grams per mole. So that's just something you have to work through enough of these examples to be able to come up with that information. So what do you think we should throw in next? Any ideas? R. Perfect. Because we don't have any other way for these things to cancel out. We don't know where to put them. So we have to use our gas constant. And remembering that our gas constant is 0.08205 atmospheres, liters over mole, Kelvin, what do you want to do? Do you want to keep it as is or flip it? Let's flip it. Okay, so mole, Kelvin goes on the top, 0.08205 atmospheres, liters goes on the bottom. Couple reasons we did that. We flipped it so that our moles would cancel, and we also flipped it so that we could get our liters in the denominator. That's exactly where we wanted them, because we've got that like that. So now it is just a canceling game, and we want our 22 degrees, which is 295 Kelvin. We want that to cancel, so we put that on the bottom. And we have our atmosphere, so that goes on the top so that it cancels. And that's it. It's like magic. It's magic math. Any answers? Perfect. Okay, so there is the first type of stuff that we're going to look at. Basically, what you need to get from this is that you need to throw in molar mass occasionally, and that's going to be in grams per mole, and then also density is in grams per liter. And what you end up seeing is if you write that off to the left-hand side, that really helps to guide your dimensional analysis so that you know what you're looking for. Okay, last couple problems. What we're going to do is we're going to work with stoichiometry. So whenever you see stoichiometry, you should be thinking about taking amounts of something, of one thing, and changing it to amounts of a different thing. So in order to do that, what do you think we always have to start with? Even before that. A balanced equation. If you're going to change from one substance to another, you have to start with a balanced equation. So this just goes through telling us stuff that we already know. You can read through that. And then here's a little reminder of our gas constant. So we read through this first one, and it says we want to find the volume of carbon dioxide that's produced when we burn octane. So let's take our octane. We're burning it. What does that mean? What do I have to do? There we go. We produce carbon dioxide. Anything else? Water. Then we come back and we balance it with a 2, 25, 16, and 18. Just like our other stoichiometry problems, I'm going to read through this and I'm going to write the information down beneath each of the substances that we're talking about. So it says find the volume of carbon dioxide, so question mark liters, produced at 1.3 atm and 125 degrees Celsius. So what we should see from that is that that's all going to be at that same condition. That's That's the carbon dioxide. We're going to do all of that there. So it's 1.3 atm, and it's 125 degrees Celsius. I'm just going to convert that really quickly to 398 Kelvin. And I know that I'm burning 75 grams of octane. So there we go. Everything we need is written down beneath it. Now we just have to think about how to go through this. What's your thought process? What do we know enough about to be able to start with? Okay, so we've got our grams of our octane. So from there, you're going to go from grams of octane to moles of octane. Then from moles of octane to moles of carbon dioxide. Now that you get it over to this substance, and of course you know your gas constant, you can easily, you've got pressure, temperature, moles, you can easily solve for liters. So that's our thought process. And there's what we're starting with. So we know grams of octane, we want to get rid of that and go to moles of octane. And there's 114.26 grams to every 1 mole. Once you get it as moles of octane, you get rid of moles of octane and go to, there we go, moles of CO2. This would be that step that I used to put the bubble around, and I'd say for every 16 moles of carbon dioxide, we have 2 moles of our octane. So we did that so that this cancels. What do you think we should think about now? Our gas constant. So here it is, and meanwhile the only unit I have is moles of carbon dioxide. Everything else canceled, so all we have is moles of carbon dioxide in the numerator. When I plug this in, how do I want to do it? As is or flip it? As it is. So I want to go ahead and have my 0.08205 atmospheres liters over mole Kelvin. I did this for a couple reasons. One of the main reasons being that I wanted my moles to cancel. The other reason being I wanted to look for my liters, my volume. That's what it was asking me for right here. So because of that, I want that in the numerator. Okay, so now that we've got it at this point, we just want to make the other guys cancel. So we've got atmospheres and Kelvin still left. We can get rid of our atmospheres by putting that down below, and get rid of our Kelvin by putting that on the top. 125 degrees Celsius becomes 398 Kelvin. We already made that conversion. Oh, yeah, this is a 1.3. I got a little sloppy with my... Okay, so that's 1.3 atmospheres and 398 Kelvin, and everything ends up canceling. This is pretty sloppy here. But everything cancels except our liters. And we do the math. And again, if you look at those values, you're going to be rounding it to 3 significant figures. And our magic answer? Good, 132 liters. Probably a lot easier like that if you just keep it all as one big problem and you don't have to do some calculations, write it down, then plug that back in. It just makes it easy to do it all as one. Okay, last one, really similar. Here, again, this is stoichiometry. The way I would notice this is it talks about mass of one thing, and then we're talking about figuring out how much it's producing of something else. So if you've got it changing substances, that's going to be a stoichiometry problem. So I see that my aluminum dioxide or aluminum oxide is decomposing. Al2O3. is decomposing to oxygen gas. And you read through there, and of course it's got to also be aluminum. Balance. And the question is, what mass of aluminum oxide? Question mark grams whenever it asks for mass. And we want to produce 46 liters of oxygen at this temperature in this pressure. So 46 liters at 32 degrees, which is the same as 305 Kelvin, and 753 torr. So in this case, we're trying to find out information about our aluminum oxide. I've got plenty of information to be able to figure out something about my oxygen. What are we going to ultimately solve for oxygen? So that we can then go to aluminum moles, right? So we want to figure out moles of our oxygen. What should we start with? What do you think would be the best thing to start with in this? I heard liters, and we could, what might be another way to do this? I'm hearing a couple different units. If you're not sure, how did we start our Pivnert problems? What did we always start with? R. We start with our gas constant. So we want to figure out moles of this so that we can go to moles of this. So in this case, you could, and in this case, you had it. The question is, can you start with 46 and do it? And the answer is yes, that'll get you there. But the reason it'll get you there is, hold on, let me write this down because I can't write and talk at the same time. Atmospheres, liters over mole Kelvin. So the reason it'll get you there is we're going to ultimately flip this. And so by starting with your liters, you're going to then flip your, it'll work because that'll cancel out. But I think it's better to start with your R because you're thinking to yourself, I want to get my moles in the numerator. So if you think about that, then that can kind of guide you. So it doesn't really matter. 0.08205. Okay, I just messed that up because I said we want moles in the numerator and I did not write it that way. So we want moles Kelvin in the numerator, 0.08205 atmospheres liters in the denominator. I did that so that I could get my moles in the numerator. So now I just see what I can get to cancel out. I'm going to put my 46 liters up here, so liters go away. I've also got Kelvin, I'll put that down here, 305 Kelvin, that goes away. I've got pressure, so I'll put that up here, 753 torr. Oops, that doesn't cancel yet, we got to keep going. So get rid of your torr, go to atmospheres, 1 atmosphere, 760 torr. So everything has canceled except for our moles. And I'm going to get rid of my gas constant here to give myself some space. That's not 46.04, it's 46.0, and then I canceled out my liters. Yeah. So we've got it to this point where everything canceled out except moles. What is this moles of? This is moles of oxygen, right? So what we just found was moles of our oxygen. So what do you think we ought to do now?
It's that step.
It is that step. We're going to get rid of our moles of oxygen and go to moles of aluminum oxide. So we look at our balanced equation. 2 goes with the aluminum oxide, 3 with the oxygen. Now we have made that big jump over to that stuff. Now that we have it as moles of aluminum oxide, really easy to just take it to grams. Running out of space, but we know that 1 mole is equal to its mass, which is 101.96. 101.96 grams. And as they're plugging in, I'm just going to write it. Here is our answer.